Hello, I'm James Christian, student R139211031, Group 18, presenting my visual effects research project. We built on VideoCoF, a CVPR 2026 highlight that unifies video editing through a temporal reasoner. Editing video is much harder than editing a single image. When you remove a person or restyle a region frame by frame, tiny inconsistencies stack up into visible flickering. The edited area shimmers and jitters across time. VideoCoF tackles this by treating editing as a reasoning problem. Instead of editing each frame blindly, it first looks at the scene, reasons about what should change, and only then generates the edit. This see, reason, edit chain is what keeps the results stable across time. The pipeline has 3 stages: see, reason, edit. A vision language reasoner inspects the source video and produces explicit reasoning tokens describing the target. These condition a WAN 2.1 text-to-video diffusion backbone, 14 billion parameters, augmented with a Fusion X LoRa. Generation uses a 4-step distilled DMD sampler, so a clip renders in about 20 seconds on a single H200. We reproduced this whole pipeline from the upstream code. We validated 4 editing tasks. Object removal erases a subject and paints the background. Object addition inserts something new, like a balloon. Object swap replaces one object with another, such as a storefront sign. And local style transfer recolors or restyles a region, like a ketchup bottle. Each has a side-by-side demo linked in our repository, and single model handles all 4, from object removal to subtle restyling. We then ran our own footage to stress the model out of distribution. A walking pedestrian removed from a street clip, an orange tabby cat added into a greenhouse scene, and doe restyled to a golden brown finish. These test background reconstruction, novel object synthesis, and texture level recoloring respectively, and all held up well.
عليكم وعفى عنكم فالآن
Next, we pushed length. The model normally edits 33 frames. We extrapolated to 128, 256, and 512. The frame budget follows a simple rule: total frames equals source frames times 2, plus 4 reasoning frames. We ran a 529 frame clip of Dayu under local style transfer, and the long edit stayed coherent. Our research extension is a temporal edit consistency evaluator. It detects the edited region using optical flow, then computes 3 metrics inside that region. Flicker is the pixel level change between consecutive frames. Flow smoothness is the average optical flow magnitude from far and back. And clip drift is the semantic distance of each frame's embedding from the first. It's a single command line script that writes results to a JSON lines file. Here is our headline result. As edit length grows, temporal consistency improves rather than degrades. Flicker drops monotonically from 65.7 at 33 frames to 20.2 at 512, and flow smoothness falls in lockstep. The temporal reasoner clearly benefits from longer context. More frames give it more temporal evidence to stay consistent. The one trade-off is clip drift, which rises slightly. Style wanders a little more over very long sequences. Breaking the metrics down by task, object removal is the hardest, with the highest flicker and clip drift, because the model must hallucinate occluded background convincingly. Local style transfer is the most stable, since it only changes color within a fixed region. The difficulty ranking matches intuition and validates that our metrics are meaningful. To conclude, we reproduced VideoCoF across 4 tasks in custom footage, scaled edits 16-fold, and built an evaluator that quantifies temporal consistency. Our key insight is that reasoning-based editing gets smoother with length. For future work, we would use the detected flow region to add a flow-guided consistency regularizer at inference time.